Now, last one on this section then, 1.10. So it says long-term responses are more effective at reducing the effects of tropical storms than immediate responses. To what extent do you agree with this statement? So what you basically need to be doing is basically saying, how do long-term responses reduce the effects of tropical storms? How do immediate responses do that? And which one do you think is actually the most effective? So some of the sorts of things you could have said on this question. You could have said that long-term responses, they reduce the effects of tropical storms by improving flood defences, by maybe forecasting when another storm is going to take place, maybe having strict building regulations to make sure buildings are suitably stable next time. And this obviously helps to reduce the deaths and damage in a future tropical storm. So not the one that's just happened, but in a future tropical storm, you'll be better prepared. So obviously the problem with this is it doesn't actually reduce the effects of a storm that has just occurred. It just makes people better prepared for one in the future. On the other hand, immediate responses, they might help by evacuating people. If we know the storm's coming, we might evacuate people, and that might therefore reduce the loss of life massively. We could also be rescuing people who are trapped under the rubble, providing emergency health care, and obviously removing dead bodies, which would therefore reduce the chance of disease spreading, and therefore a secondary effect of people dying of disease. That would reduce that as well. Obviously the problem with immediate responses is that they don't actually reduce the damage to buildings and infrastructure. We're just sort of responding to the damage that has been caused. And it won't really reduce the effects of tropical storms in the future. It's just trying to reduce the damage caused by the one that's currently happening. So once you've talked about some of these long-term and short-term responses and how they may or may not help, you need to then sort of decide whether or not you agree with the statement. So you need to have a conclusion that says, I agree with these statements to a large or a small extent because, or I completely disagree with the statement because. And as I've put here, if you want to get top marks in this question, you also need to have some specific examples. And if you remember, we did look at Typhoon Haiyan. So if you've got some examples of the long and short term or long and immediate responses in that particular case, that would also improve your answer. But as I say, you definitely need a justified conclusion that answers this to what extent part of the question, if you want to get anywhere near top half of the marks in this question. First section done. Now we're on to coastal landscapes in the UK. Now here we are then, question 3.1. Now this is going to involve a bit of map skills, which if you had no idea about, we might need to spend a little bit more time practicing after we've done this. So 3.1, it says, give the 4-figure grid reference for the grid square in figure 11 that features Elbury Cove. Now if you look closely, it might be better looking at your one. On here it's Elbury Cove. Now if you want to find this square, we need to find the bottom left corner of this square. So that square needs that point there. So we go along the corridor to 90 and up to 57. So 9057 will be that square there. So that's the answer. And that's how you do it, 9057. Now, this next one, 3.2, it says, what's the difference in height between the spot height at 914,542 and the spot height on the golf course at 908,568? Now, this is going to require you to be able to do 6-figure grid references. So you need to find these two locations and find the height of these two locations. So if we're trying to find 914,542, 914 is about here. So 915 would be here. 914 is just less than that. And we want 542. So 54 and just about 2 up is there. So you'll notice it says 150. So that point there is 150 metres above sea level. Now we want 908,568. So 908 is about here. And 568 is also about here. So we've got a spot height there of 59 metres. So if you take those away from each other, you get 91 metres. So that's your answer to that. Now this next one says, study figure 12, a photograph taken at 931,549 in figure 11, with the photographer taking a photograph from, well, in the northeast direction. So 3.3 says, using figures 11 and 12, name the headlands shown in the photograph. So So first we've got to find this point where they took the photograph from. So 931,549. So 931 is about here. 549 is here. So that point there is where they've taken that photograph from. And they're looking in a northeast direction. So northeast is sort of that way. So they're stood here, facing sort of that way, and they're obviously looking at a headland, so that sticky out bit of rock basically from the sea, protruding out into the sea. So if you look northeast, you can see this here. It says Durl Head. So that photograph, it's got to be of Durl Head. So that's your answer there. Now it says, suggest one reason why the headland and bay shown in figure 12 have formed on this stretch of coastline. Now if you've done some revision, you might know that a headland and bay is formed when there are alternating bands of resistant and less resistant rock. So this layer of resistant rock here is eroded far slower than the rock that used to be here. So therefore that protrudes out to sea, and the rock that used to be here has been eroded backwards inland, creating this bay. So we've got hard resistant rock, some soft rock that used to be here, and then we've got more hard rock at this side of the photograph. So there's your answer to that one. Now, as we were saying, a headland is formed due to the erosion of less resistant rock next to a layer of hard resistant rock. And for question 3.5, it says, which one of the following coastal processes is not likely to have contributed to the formation of the headland in figure 12? Well, the only one that isn't really to do with coastal erosion or weathering is longshore drift, because that's to do with the transportation of sediment along the coast. So that one there is your answer. Moving on quickly to 3.6, it says, study figure 13, a sketch map showing part of a coastline where deposition is the main coastal process. And it says, suggest how the coastline shown in figure 13 may change in the future. Well, the important thing to note here is we've got a beach and we've got a bay here, and it tells you the direction of the prevailing wind, and that's a really important thing here. It's showing you that the wind's coming in at that direction, which therefore means that so will the waves. The waves will be coming in that direction. So hopefully you might take a guess and say that the waves might start to make the beach extend outwards in front of the bay. And if you have a look here, this is the sort of thing you could have said. So it says the beach may continue to extend northeast, which is, as you can see, north is there, so extend that way. The beach will continue to extend northeast due to longshore drift, and that will form a spit, which, as you can see in this diagram here, if it extended outwards, it would form a spit. And the sheltered area behind the spit may cause material to accumulate, so you'll have slower water with less energy behind the spit, and that will lead to deposition of material, which can create a sheltered area, which could become a mudflat or a salt marsh. If this wind direction here changed direction, it might suddenly start going in that direction, that would cause the spit to sort of curve round at the end. So the ends of the spit could curve with strong winds and waves. And if the spit actually reached the headland at the other side, the spit could actually extend all the way out and reach the land at the other side, then it'd be called a bar. And the water behind that might form what we call a lagoon. So if you say some of the things we've just talked about, that'll help you get some marks on that question. Now look, they've treated us to another figure. So it says study figure 14, photograph of coastal defences at, I'm not even going to try and pronounce that, in North Wales. So it's using figure 14 and your own knowledge, explain the costs and benefits of hard engineering strategies for coastal management. So we need to look at what sort of coastal strategies we can see in figure 14 and say what is good and bad about those strategies, and then maybe include a few more strategies of our own. So hopefully you might know that these walls of wooden walls, barriers out to sea, extending at right angles to the beach, are called groins. And as I've got here, so groins trap sand, preventing longshore drift, and that helps prevent the waves from eroding the coastline. So these barriers called groins are stopping the sand from moving along the coastline and sort of keeping it in place to form the beach. And this beach is then protecting the road and the houses behind, because the beach slows down the waves and reduces the energy of the waves. Another good thing about groins is that they're quite cheap. However, as we're looking at costs and benefits, we need to make sure we say that some of the costs might be that they need maintenance, so they sometimes get damaged and they need money to repair them. and they also potentially don't look that attractive, so they have a negative visual impact. Another coastal engineering, hard engineering strategy you might be able to see is we've got a sea wall. So we've got a concrete wall which helps protect the coastline as well. And this is effective against erosion, but the cost is that it's really expensive. It could cost millions and millions of pounds. And again, it's not that attractive, so it's a bit unsightly. So that's the ones that you can see in figure 14. In order to get full marks on this question, you also need to use your own knowledge. So a couple more strategies you might mention. You could mention rock armour, which is this, what I've got in this photograph here, which is where you just place big boulders at the bottom of the cliff to help absorb the energy of the wave in a similar way to a sea wall. And this obviously does protect the cliff, but it's potentially unsightly and it might need replacing. However, it is a bit cheaper than a sea wall. Could even mention gabions, which are basically similar to these, so it's just boulders, but this time they're put inside metal cages. So it's kind of like a sea wall, but just a cheaper version. So you just need to make sure you talk about what you can see in figure 14, plus a few of your own. Make sure you talk about costs and benefits.